Right. Okay, so today we have Shai Chester from Imperial College, and he will tell us about monopoles, duality, and deconfined quantum tricriticality.
All right, thanks for the invitation. This is based on a paper I had a couple years ago by myself, and then a paper with these two condensed matter physicists, and then a recent paper with Ning Su. Let me start with the idea of IR duality, because there's many notions of duality. So IR duality is when you have two quantum field theories that are different at small scales, what we call the UV, which could be like a lattice, for instance, but they become the same formal field theory at large scales, which is what's called the IR. So usually one of these formal field theories is weakly coupled in the regime, with the other is strongly coupled, or they're both strongly coupled. The point is, though, is that it's rare that both are weakly coupled. And that's what makes it non-trivial. Otherwise, it'd be kind of silly if they're both weakly coupled. So in particular, maybe a more intuitive way of explaining it is that you can say that classically, without quantum mechanics, each theory looks totally different. But due to quantum effects, the theories magically become the same. And this is why it's an interesting concept, because it's a quantum concept. Since at least one theory is strongly coupled, it's hard to check these dualities. So in particular, when the space-time is bigger than 2, I mean space-time, not space, as in condensed matter, then you almost always need supersymmetry in order to check these dualities. So for instance, the original kind of classic duality in 4 dimensions with n equals 2 supersymmetry by Seiberg, and then this was generalized to various supersymmetric dualities in 3 dimensions. And in these cases, you can in some cases prove them, in other cases find not very non-trivial evidence using supersymmetry. But it's good to remember that we live in a world without supersymmetry, at least as far as we know. And so it'd be nice to find dualities which do not involve supersymmetry, which can be relevant to actual experiments. And so the classic duality, dating back to the late 70s, is this particle vertex duality. So this says that if you have quantum electrodynamics in 2 + 1 dimensions, one complex scalar, and this is dual in the IR to the critical O2 Wilson-Fisher theory. So this actually is experimentally relevant because it describes continuous phase transitions between the superfluid and mod phase of both Hubbard model and integer filling on a 2D lattice. And apparently this duality actually has direct experimental implications. I guess like the main implication being that it would have originally been extremely hard to study this theory because it's some kind of strongly coupled gauge theory, but because it's the same thing as the Wilson-Fisher theory, which we know pretty much everything about, thus it allows us to make predictions about superfluid phase transitions. So I guess it's an interesting thing. So why do people believe this duality is correct? Now, I don't know why they thought it was correct back in the 70s and 80s, but the only evidence I find convincing is actually from the 2000s, which is that you could do lattice simulations for both models. So you have one lattice that flows to the Wilson-Fisher, that's easy. You have some other lattice that flows to this quantum electrodynamics, that's a bit more challenging. This is why it took until the 2000s in order to do this. So this is the Wilson-Fisher guy, this is the QED3 guy, and then you can just compute critical exponents, or what we like to call scaling dimensions, using these lattice simulations. And so here are some values for the lowest few operators of charge Q under this O2 symmetry. And as you see, these values are extremely close, at least to the level of accuracy that lattice is capable of. And so to me, this is the most compelling evidence that this duality is correct. So recently, there's been different versions of non-supersymmetric dualities that have been more interesting. And so these were proposed in the last 10, 20 years. So these dualities are nice because they relate a theory with fermionic degrees of freedom to another theory with bosonic degrees of freedom. So for instance, one such duality is that quantum electrodynamics now with one complex fermion, the short time level -1/2, is supposed to be dual to the critical O2 model. And so this duality is called 3D bosonization because you could say it's kind of like roughly spiritually similar to 2D bosonization in the sense that you're relating fermionic degrees of freedom to bosonic degrees of freedom. But of course, in practice, it's actually extremely different. Because what we call 2D bosonization is some kind of exact duality along the entire RG flow. So another way of saying it is it's kind of like a rewriting of variables, which from my perspective is actually a bit more trivial because it's just some kind of like classical rewriting, a field redefinition, as it were. Whereas in 3D bosonization, this is IR duality, which is something which is kind of purely due to quantum effects and is something which is extremely surprising. So that's why I wouldn't take the word bosonization too seriously. Another such example of this duality, which has been proposed, is a fermion-fermion duality. So this relates QED3 with one complex fermion, in turn time is level 0, which you have to define carefully, to a theory of a single free complex fermion. And this one apparently has some experimental implications because it describes the fractional half-filled fractional quantum Hall effect and phase transitions thereof. And apparently, if you have this duality, then it would imply certain properties of that phase transition. So with all these dualities, though, it's very hard to check them because with particle vertex, you could do lattice simulations on both sides. But once you have fermionic degrees of freedom or Chern-Simons level, it becomes much more challenging to do a lattice simulation because there's like sign problems. And so this is why so far I would say there's not really such compelling evidence for these dualities. So in fact, there's actually a whole web of dualities which people have proposed, and they're all kind of connected to each other. It's shown by these authors a few years ago. So particularly, you can define these two operations called S and T. The S operation is you take a theory and you gauge the global symmetry. The T operation is you take the theory and you shift the Chern-Simons level by 1. And so you can apply this to the Lagrangians of, say, two dual theories, and then they will give you new dualities. So for instance, let's go back to this duality we were describing before. QED3 with one complex scalar, Chern-Simons level 1. This is supposed to be dual to one free complex fermion. So in this language, we would say you start with the free scalar, you act with T to get Chern-Simons level 1, you act with S to turn it into a gauge theory. So then on the left-hand side, you have QED3 with one complex scalar and Chern-Simons level 1. And on the right-hand side, fermion just means free fermion. And so to derive a new duality, let's act with S inverse and T inverse on both sides. So now on the left-hand side, we have scalar, which actually denotes Wilson-Fisher scalar. And then this is supposed to be dual to fermion, which we have now gauged and shifted to Chern-Simons level. And so this is the duality we described in the previous slide, which was QED3 with one complex fermion and Chern-Simons level -1/2 is dual to Wilson-Fisher. So this is an example of how you can derive one duality from the other. Now I should note that this derivation is not rigorous because this S and T move is something you apply in the UV to the Lagrangian, whereas these dualities are in the IR. So these derivations are more suggestive than they are, actual full derivations. So one way people try to find evidence for these dualities is that you can check that the Tuft anomalies are the same for each putative dual theory, because Tuft anomalies have to be the same along the entire RG flow. But it'd be nice to get like evidence on the level of scaling dimensions, kind of more dynamical evidence, such as one had for particle vertex. So because we can't do lattice simulations, instead people have tried to find evidence through other means. So one thing you could do is you could consider some generalization where you have QCD3 with n colors, as well as NC colors, n scalars, Chern-Simons level K. And so this was proposed to be dual to this other variation of QCD3. This is by Aharoni back in 2016. And then in this theory, in the large color and K limit with fixed ratio, you can actually do calculations. It becomes analytically tractable. And so people were able to check various dynamical quantities in this limit. But this is very far from the limit we care about. I mean, we care about one color, whereas this is a duality for a huge number of colors. And if you just take the answers in a large color expansion and extrapolate down to one color, you get crap results. So clearly it does not extrapolate. Another way people try to prove these dualities is that you could take the supersymmetric versions of the dualities and try to flow to the non-supersymmetric versions that we see. This is again suggestive, but it's not a proof because the flow could be supersymmetry. And then finally, you could take lattice descriptions, which are putatively flow to each of these theories, and then show that they're kind of exactly the same on the lattice. But again, this is more suggestive because the flow is always in control. Okay, so in this talk, we're going to check these dualities by computing multiple operator scaling dimensions and a large flavor Chern-Simons level expansion, and then extrapolating this down to one flavor. And we will actually find this extrapolation works incredibly well, much more than you would expect. And this is how we get evidence for all of these dualities. So particularly, we're going to start by defining what we mean by monopole operator. Then we're going to describe this large flavor expansion. Then we're going to compare it to operators in the dual theories and find a precise match after extrapolating the flavors as well as the Chern-Simons level. And then finally, we are going to combine these large flavor expansions with some bounds from the conformal bootstrap to argue that the n equals 2 theory, which is called the CP1 model, which is conjecture in the past to be the simplest example of deconfined criticality, in fact, is a tricritical CFT, which resolves kind of like a decades-long question in condensed matter physics. So that will be the exciting ending. Okay, so let's start with the definition of conformal QED3 with complex scalars. So here you have an action in 3 dimensions. So you have a field strength for your U1 gauge theory with coupling E. You have scalars phi. You want to have a Hubbard autonomous field sigma. This is how you encode the interaction. So instead of having a phi to the 4, we can have a sigma. The coupling has its own coefficient lambda. And then you have a conformal mass, and then you have a Chern-Simons level here where K has to be an integer. And when K is 0, this is called the CPN model, because you can think of it as a nonlinear sigma model on this manifold. So when the number of flavors is large, you can actually prove, as it was done back in the 80s, that the theory floats an interacting CFT in the IR. This is believed to hold for finite values of n, but it's a very contentious question for what values of n it does hold. And some people claim it is not a CFT for certain values of n. Anyways, assuming it is a CFT, then when you flow to the IR, because these two operators are irrelevant, they have UV dimension 4, thus their couplings go to infinity, and that means in practice you can just ignore them in the action. So these first two terms you can ignore. So what are the operators of this theory? So one type of operator you can construct of the fields that show up in the Lagrangian, which is phi, sigma, and a. Those are more conventional operators, and then you can compute their scaling dimensions in a large n expansion using Feynman diagrams as done in ancient times. But we are more interested in another class of operators called monopole operators. So these operators are charged under a different global symmetry. So unlike the SUN global symmetry, which just rotates the scalars, there's a U1 global symmetry. And this is because you have a gauge theory in 3 dimensions. And so the Bianchi identity implies you have a conserved current, defined as the dual of F, which is conserved. And so all fields in the Lagrangian are uncharged under this U1 global symmetry. And so the operators that are charged under it, we kind of define them to be monopole operators, which are not written in terms of fields in the Lagrangian. Whereas we normalize the charge to be in half integers, which is given by Dirac quantization. So when the Chern Simons level is 0, as we will see, these monopole operators are scalars and singlets under the SUN flavor symmetry. When the Chern Simons level is non-zero, though, we will find that they're in non-trivial representations of the flavor symmetry. Anyways, the point, though, is that you can also compute the scaling dimensions of these monopole operators in a large flavor expansion. This was originally shown back in 1990, actually, through a very hard calculation in flat space. The method we use, though, is the more modern version from the early 2000s by Kapustin et al., which uses the state operator correspondence. Okay, so let's discuss this method of computation. So the state operator correspondence relates operators in flat space to states on the cylinder S2. So in particular for monopole operators, states with 4 pi cube magnetic flux on the cylinder correspond to monopole operators on flat space. So that means if you compute the energy on the cylinder, this will give you the scaling dimension in flat space. And so that's kind of the basic method. So one thing to notice is that when you have a Chern-Simons term, this will contribute 2qk to the Gauss law constraint. And so this means that the vacuum will no longer be gauge invariant, which means you have to dress the vacuum with matter to make it gauge invariant. And this is why when the Chern-Simons level is non-zero, these monopole operators will end up transforming in non-trivial representations. It's due to this dressing. So in practice, what we're going to do is we're going to compute the thermal free energy defined on S2 cross S1 with radius inverse temperature with 4 pi Q flux, and then we're going to take a small temperature expansion. The reason why we go to finite temperature is because this is actually necessary in some cases to regularize various divergences, but also it will teach us about entropy and other kind of interesting things. And so this was first done in this paper, I guess, some years ago with Silviu and various other authors. And so what's going to happen is that after we integrate out the matter to compute this free energy, we're going to find that the free energy scales with n, which is why we're able to do a large n saddle point approximation. And so this is a very different kind of calculation than Feynman diagrams. Because for Feynman diagrams, for some operator which is not a monopole, the expansion goes like n to the 0, then 1 over n, et cetera. This expansion, the leading order is going to go like n. So in some sense, these monopole operators are like black holes, and in that they scale with n. Another nice thing about doing this thermal free energy calculation is that by looking at the subleading and temperature terms, it's going to tell us about the degeneracy of states, which will tell us the representations of the monopole operators that we find in this thermal path integral approach. Okay, so let's begin with the calculation. So we start with the action, we integrate out these scalars phi, and then we get this for the partition function. So we get this kind of differential operator, which was the original kinetic term for the phi's, and then the Chern-Simons level just kind of goes along for the ride. Also, sigma shows up there. So we want to compute this with the saddle point approximation. So everything is multiplied by n. We define kappa to be k over n. So let's consider a saddle point which satisfies the properties we want. So we want the field strength to integrate on the sphere to 4 pi q. And so we can take a saddle point value of this form. And then for the Hubble-Stanovich field, it's just going to be some expansion around some classical value mu. Finally, in the tau direction, because we're on S2 cross S, we have this holonomy, which you can also think of as a chemical potential term. And so this is our ansatz for the saddle. And now let's try to fix the values of the saddle, i.e. let's try to fix alpha as well as mu, because everything else is fixed. So we're going to plug in the ons-outs for the saddle into this quantity. This will give us the leading large n term. And then you do this evaluation, and you get this kind of sum over Matsubara frequencies over here, where lambda is the eigenvalues of this operator, d is its degeneracies on S2 cross R with 4 pi q close. Okay, so this is the expression you need to evaluate to get the leading order answer. But first, we want to fix the values of alpha and mu by taking the saddle point equations, which take derivatives of alpha and mu, demand they are 0. When you solve for alpha, you actually find there's a unique real saddle, which takes this form. So basically, the saddle is that alpha has to be the lowest eigenvalue, because these eigenvalues can go from q up to infinity, so we take the lowest one. And then there's also this kind of temperature correction, and then everything else is exponentially small in temperature. And then to get the mu saddle, you just plug in alpha, and you get this kind of non-linear equation, but you can solve this equation numerically. There's actually one case where you can solve it analytically, which is the special case when 2 kappa equals dq. In that case, mu equals q squared is an exact solution. Otherwise, you just solve it numerically. Okay, so after solving these values numerically, you plug it in, and then you can compute the thermal free energy, which you can expand to temperature. The leading term is the energy, which is what we identify with scaling dimension. Subleading term is the entropy. And so this is what the answers look like, fairly simple. And we will give some kind of microscopic interpretation of why we get this answer in the next couple of slides. But for now, this is just the answer. It's this infinite sum plus this term, and then this term for the entropy. For this special value of kappa, because you can do things analytically, you actually get this very simple answer, but I don't really have an intuitive explanation for why you get the simple answer. But it's kind of curious that you get a simple answer in that case. Well, one of the reasons why this happens basically is that the value of Q kind of cancels out the value of the chemical potential. Or sorry, not the chemical potential. The Hubbard-Shatanovich field saddle point cancels out the contribution, you could say, of the magnetic flux, and this is why you end up getting a simple answer. Anyways, okay, so now for the subleading calculation, which is much more challenging. So there you have to consider fluctuations around the saddle point. So basically you expand your path integral to quadratic order in the fields. There's a little trick where to cancel gauge modes, you divide by the Q equals 0 guy. And then the whole challenge is to compute these kernels, which is the coefficients of these quadratic fluctuations. And these are all going to be written in terms of the Green's function. This is the Green's function on S2 cross S in the presence of magnetic flux. So it's a fairly complicated quantity. Thankfully, it can be computed using monopole spherical harmonics, which we did in this paper in 2017. And again, for the special value of kappa, you can actually write it in closed form, which is what I did in my more recent paper, which is what originally allowed to do this calculation, because the closed form solution was very useful for checking things. Okay, so in particular, you integrate out these quadratic fluctuations, and then this is the answer you get to subleading it in. So you get a ratio of these kernels, and then you're kind of summing over all these harmonics as well as all these Matsubara frequencies. And then you can expand this in small temperature to get the scaling dimension, but you could also get subleading terms in temperature. Now, this is where the working at finite temperature becomes important, because you'll notice that there's terms that look like log temperature, which means if you had worked at 0 temperature to begin with, you would have gotten divergences, which don't make sense. But there's actually an explanation for why you get these log temperature terms, which I'll explain in the next couple of slides. Anyway, so this is your final answer for the subleading order. It's a very complicated integral and sum, and so in practice, you just numerically compute it using some cutoffs, and you're able to get an answer that converges. And the non-trivial check is that you don't get a logarithmic divergence, because if you have any typo at all, you get a logarithmic divergence. Okay, so what's the subleading result for the temperature-dependent terms? So this is what you find for the temperature-dependent terms, up to exponentially small in temperature. And so the subleading in end term for zero transcendence level was actually computed previously in this paper by 2015. The main novelty of these recent papers is that we did it for non-zero transcendence level. I should also note that the large Q limit was also computed just by doing this calculation for many values of Q. And this actually gave the first check of the large charge expansion. So in particular, they were able to check the Q to the 0 term, which is supposed to be universal. So the story is that originally this calculation was generalized to the specific value of kappa, where things simplify in my single author paper. And then we did the most general case of kappa and Q in this more recent paper, which is much more challenging. Okay, so now let's give a microcanonical interpretation of these answers that we have found. So what's the idea of a microcanonical interpretation? So the idea is that you want to use some kind of oscillator construction. And this is actually only valid in the UV when E squared times N is going to 0. And so it's not obvious that such a construction should actually remain valid in the IR CFT, because in that case, E squared times n is going to infinity. And so I would say this microcanonical interpretation is a bit conjectural, but the reason to believe it is that it actually matches our thermal results. But the point is that it's not obvious that it had to match the thermal results. And anyways, so for scalar Q and E3, let's imagine expanding your scalar field phi in modes on Lorentzian S2 cross R. And so you would get the kind of usual modes, one for each value of J, where J goes from Q to infinity. So the energy is just this eigenvalue, which we discussed before. These modes will have spin J, they'll have a certain gauge charge, they're the fundamental of SUN and a certain degeneracy. And then the vacuum has a Casimir energy, it spins 0, and it also has a gauge charge when the Chern-Simons level is non-zero. And so this is related to the fact that you have to dress with these modes in order to cancel this gauge charge when K is non-zero. Now, this isn't exactly a free field limit because these eigenvalues actually depend on the saddle point value of the Hubbard-Shatanovich, so it's more of a mean field likely. Anyway, so recall that the answer in leading order in N was this. So how can we interpret this now? So the interpretation is that this first term is a Casimir energy, and so this corresponds to the fact that we have this vacuum. And then the second term is the modes that you have to dress the vacuum with to get a gauge invariant answer. And so that's why the second term you only have when K is non-zero. So this gives a very nice, simple explanation to this energy. For the entropy, it turns out that this is the entropy of every possible way of contracting the indices of these modes that you have dressed the vacuum with. Because the point is that like to kill the gauge charge, any like combination of modes works. You just have to have that number of modes. So to give an example, imagine the case of SUN cross SU2. So like this works specifically when DQ equals 2. So then the different ways of contracting the indices would give these kinds of representations. So you would have every possible SU2 spin. I mean, this is the Lorentz spin. You'd have every possible spin going from 0 to NC. And then for those spins, you have this corresponding representation under the rotational symmetry given by this Young tableau. And so if you take the logarithm of these representations and you look at large N, then in fact you get precisely this answer. And so this is kind of a nice check. And so basically what's going on, the point is that at large N, there are many degenerate monopole operators. And they all have the same large N energy, even though of course we know at finite N that this should not be the case. Okay, so now let's give a microcanonical interpretation to the subleading and temperature terms. So because we know that there's like infinitely many operators of the same energy when N is infinity, thus you should conjecture a continuous density of states. And so let's imagine the free energy is written in terms of this continuous density of states. Then if you compare this ansatz to what we actually find from the thermal calculation, then you can kind of match this density, and you find the following answer here. And so you can then use this continuous density of states to compute the energy splitting, which depends on the spin. So this Y is basically proportional to the spin, normalized by N. And so this kind of tells you how these degenerate operators, how they become non-degenerate at subleading orders in N. As one would expect, because of course at finite N, these operators shall be do. So this explanation also, yeah.
Are there or are there not log terms? So
there are.
is alpha minus 1 or not?
No, so there are log terms. So alpha is not -1, and there are log terms. So thanks for pointing it out. And having log temperature terms is generic when you have like infinite operators in some limit. So actually the same thing happens in the SYK model. So it's like when you have infinite degenerate operators in some limits, for instance at large N, then it gives you a logarithm in the entropy. So this
You just said before that you wanted to cancel the log terms. That's what
No. I don't want to cancel. I wanted to explain them. So basically, the point is that if you had worked at 0 temperature to begin with, you would have gotten these weird delta functions in your answer, delta function of 0, which wouldn't have made sense. But when you work at finite temperature, you now have an explanation for why you're getting these terms, because they are naturally explained as due to the fact that you have infinite degenerate operators in this limit. And so they are there, and they should be there, and they are given by this simple ansatz. And then reading off the coefficients of these log terms tells you what this energy splitting is. So it's important that they should be. This was something back when we were writing this paper, we were confused for like 6 months until we figured out why it makes sense for these log terms to be there. Anyways, okay, so that concludes the description of the calculation. So even if you didn't follow all the technical details, that's okay, because now you can just wake up for the answer. Okay, so now let's actually use these results to discuss these dualities. So let's first consider particle vertex duality. So here we're going to extrapolate n to 1, and then it's supposed to be dual to critical O2 Wilson Fisher. So in this duality, monopoles of charge Q are supposed to be dual to the lowest dimension operator made out of two Q complex bosons phi in the Wilson-Fisher theory. So for instance, 1 phi would be the lowest monopole, 2 phi is the second lowest monopole, etc. All these operators are unique scalars, because of course they have different dimensions. And so you don't have to worry about any kind of degeneracy, which makes life simpler. And also people have computed on the Wilson-Fisher side these operators for many different values of Q. So when Q is smaller than 2, they were computed to high precision in this bootstrap study. But even for bigger values of Q, they've computed to slightly lower precision using this lattice method developed by these authors recently, which allows you to go to kind of like huge operators, which itself is very interesting, because previous lattice methods couldn't get such high dimension operators. Anyways, so now let's do the comparison. So this is the table for everyone to pay attention to. So even if you didn't understand where this came from, just understand the results. So the first column is the leading large n term. The second column is the subleading large n term. And because we're setting n equals 1, we're just adding these two columns. And so this is the prediction from the large flavor expansion. This is the dual operators in the Wilson-Fisher theory. Blue for bootstrap, red for lattice. And as you see, they are shockingly similar to each other. So you see the relative error for Q equals half is just 2.5, which is quite small. And it gets a little bit bigger, but even all the way up to Q equals 5, the error is still just like 6%. So which is very surprising. It's especially surprising because the subleading term is actually bigger than the leading term. And so you would think that this expansion is very non-convergent, yet nonetheless, including these first two terms, gives this amazing match. And so this is kind of magical, and I don't have an explanation, but it clearly works.
How close is the degeneracy?
Sorry. Question?
Any chance to check the next term in the expansion and see that this is very...
I would love for someone to check the next term in the expansion. I hope someone is motivated to do that. Your question?
Yeah, how close is the degeneracy to 1?
How close is the degeneracy of what?
Well, you just told us how to calculate the degeneracy of the monopole.
So there's actually no degeneracy when Chern-Simons is level 0. Because the degeneracy has to do with the fact that when there's Chern-Simons coupling, then it's gauge dependent, you have to address with modes. In this case, you don't have to address with anything, and so this is why the monopole is unique. So this one makes the calculation a bit simpler. So this is a much cleaner calculation. And yeah, so it's kind of miraculous that it matches particle vortex duality so well. Okay, so in fact, this miracle works not just for n equals 1, but for every value then. Because you could do lattice simulations for QED3 with n complex scalars.
Another question. So how heavy is the next monopole of charge, the same charge? So imagine you take the first excited.
That's also an excellent question. It'd be so I have a couple students who have claimed that they will be computing the excited monopoles. They've been making that claim for a year though. So I think they need to be better motivated. But I think it'd be a very important calculation to do.
Do you have any guess though? I mean, because you're going up to very high scaling.
It's really hard to say. I mean, it's like, okay, at leading large end, I guess you know what the answer is because you're just going to be dressing with some modes to get the best excited state. But like, at least, from this calculation, it seems it's very important to have the subleading term. If you just had the leading term, you wouldn't even know, you wouldn't even get remotely close to the answer. And so this is why I don't trust to say what the answer is until I know the subleading term. I mean, it could also be this won't work. It could just be like, this is a miracle that works for the lowest one. But I mean, it's certainly worth doing this calculation and checking. Because you would have checks, from the bootstrap, the next excited operators. So anyways, so this match also works for larger values of n because you do lattice simulations for larger values of n. People have done those. And so this was a plot from Silviu and Sevier's original paper. So this is the monopole operator scaling dimension normalized by n. So it's a line. And then you're matching it against various lattice estimates for different values of n. This is x-axis is 1 over n. And as you see, it kind of roughly matches for all these different values. And so it just seems that this large n expansion, for reasons that aren't fully understood, is just an amazing expansion for all values of n and for all values of q. Okay, so now let's apply the large flavor expansion to a more interesting example. Because particle vertex we already kind of knew because we do lattice simulations. But this 3D Boltonization, we can't do lattice simulations, so we're not trivial. And so in particular, we're going to try to compare scalar QED3 with n equals 1, k equals 1 to a theory of a single free complex fermion. So in particular, the monopole operator with charge q is dual to a lowest dimension operator made out of 2 q fermions. So in particular, they're going to be half integer spin when q is half integer. So for instance, the lowest monopole will be a single fermion. Second lowest monopole will be 2 fermions, etc. So for these lowest dimension cases, the operator is unique because there's only one way of contracting the indices, and it has spin 0. But for higher q, because of theory of fermions, you have to start addressing with derivatives to get a non-zero operator. And so already starting with Q equals 2, where you have 4 fermions, you have to start addressing with 2 derivatives, and there's 2 different ways of contracting the indices of those derivatives. This is why you get degenerate operators. So they both have dimension 6, but one has dimension spin 2, one has spin 0. And so this is a subtlety, even in a free fermion theory. So how do we count the operators, taking into account this subtlety? So one way of doing it is that you compute the spectrum of the free fermion theory by looking at the free energy on S2 cross R in the presence of some background U1 flux. So to compute the spectrum, you have these eigenvalues of the fermion operator, which is just spin J plus half. And then you're basically going to be like dressing the vacuum with these modes, and every time you fill an energy shell, something special will happen. So in particular, a filled energy shell corresponds to an operator which is a unique scalar, whereas unfilled energy shells will either not be scalars or will not be unique operators. But the filled shells, which are the special ones, so this only happens for special values of Q, so when Q equals 1, 3, 6, 10, etc. And then it gives the corresponding scaling dimensions, which can be written in closed form, which takes the form like Q, square root of 1 plus Q. And so this is a very simple answer for these special values of Q. For other values of Q, the pattern is much more complicated. There's some kind of like oscillation. And so it's only for these kind of unique scalars that you get this simple answer. Okay, so now let's compare the answers in the free fermion theory to what we get from this large flavor expansion. So a similar table as before. So first column is leading order large n, second column is subleading order, third column we add them together, then we compare the fermions, which are all integers, then we look at the relative error. So let's first talk about the purple values. So the purple values, as you see, match incredibly well. So in fact, they match even better than the particle vertex example. So the worst match is for Q equals 1, where we compare 1.95 to 2. But as Q gets bigger, the match gets better and better and better. So for instance, once we get to Q equals 21, our prediction is 180.5, and the exact answer is 182, which is quite a match. I mean, this is a relative error of less than 1%. And in fact, it seems like the relative error is going to 0 as Q gets bigger. Although it becomes harder and harder to do our calculation as Q gets bigger. So this seems like a magical match. I would even argue perhaps that this is like the best example of a perturbative expansion in physics, in that just by including 2 terms, you're able to match a prediction to less than 1% relative error. I mean, I don't know of any other such example. So the obvious question though is that, like, why are we only looking at the purple values? What's wrong with the black values? So the black values are like the operators that are either not scalars or are not unique.
Sorry, next question. Can you give an explanation of why for large Q here it seems to go better and better, but in the other case it was worse and worse?
I don't know. It's a mystery. I mean, I'll have a couple comments about it though in the next slide. Okay, so first of all, let's talk about these black values. So the operators in the free fermion theory that are not unique scalars don't seem to match the monopole calculation so well. So for instance, our prediction would be 0.72, the answer is supposed to be 1. Huge error. So it might just be that the monopole calculation is just invalid in these cases. Because first of all, if the monopole is not a scalar, then maybe the saddle we chose was just the wrong saddle. Because I guess we chose some kind of saddle, they're spherically symmetric. Maybe there's some other saddle which breaks spherical symmetry, which is more appropriate for a spinning monopole. It could also have something to do with like the fact that now the Chern-Simons level is non-zero, you have this degeneracy, there's like a degeneracy breaking term that depends on the spin. Maybe you have to take that into account, and maybe that corrects the answer. Although, like, at least my attempts so far, that didn't work. But all those could be explanations. But there's actually a curious thing we observed, which is that take in the free fermion theory, this formula, which is only supposed to apply to the unique scalars, which only applies for very special values of Q. So take this formula and analytically continue this formula to the values of Q where it's not supposed to hold, which for instance, Q equals half, for the non-unique or non-scalars. When you do that analytic continuation, and then you compare to the large flavor expansion, again, the large flavor expansion starts giving good answers. So for instance, this formula with Q equals half gives 0.74, and our prediction was 0.72, et cetera. So of course, this is not the physical answer. The physical answer for Q equals half is 1. But what's kind of intriguing is that it seems like this formula, while not the physical answer for these bad values of Q, nonetheless is matching our large flavor expansion. And so what this suggests is that the large flavor expansion might just be capturing the effective large Q theory, which as shown by these authors recently, only applies to the unique scalars. And so this is kind of the connection to the large charge expansion. So a large charge expansion gives some effective theory. It's only supposed to apply to the special values of Q. When it applies, it gives this answer. And so maybe for some reason, our calculation is just probing this large charge effective theory, and thus it gives the answer for every value of Q, which in some cases is physical and in some cases is not physical. And this might also explain why the mass gets better and better as Q gets bigger. So this is all, I think, kind of intriguing evidence, but I don't yet know how to make a more precise argument in this regard. Okay, so that concludes our discussion of this match of 3D bosonization, which I should emphasize is the first dynamical evidence for 3D bosonization. So now let's move on to our last topic, which is deconfined quantum criticality. So standard Landau-Ginzburg phase transitions, the story is that you have some symmetry G, which is preserved in one phase and then broken in the other. So for instance, the Wilson-Fisher model describes phase transitions. You have a phase that preserves ON, another phase that breaks ON, and then a CFT in the middle. Phase transitions, though, that are described by QED3 when n is bigger than 1 violate this paradigm, because what happens is that you have the two symmetries, SUN and U1, and what happens is that one phase preserves SUN, breaks U1, and the other phase is vice versa. So this is what's called the beyond Landau-Ginzburg phase transition. And so this is why people are so interested in this so-called deconfined quantum criticality. The deconfined term, I think, corresponds to the fact that you have a gauge theory at the phase transition. And so particularly these gauge fields are emergent at the critical. And so this thing was first proposed, I guess, back in the early 2000s by these authors who were all at KITP this past week. So the simplest example of this deconfined quantum criticality would be when n is 2, because n needs to be bigger than 1. And so in particular, it's QED3 with two complex scalars turning time is level 0. So this is called the Neal VBS phase transition. The Neal phase breaks the SU2, the VBS phase breaks the UI. And this is actually realized by quantum antiferromagnets on a 2D square lattice. Okay, so people have studied this theory using lattice simulations. And so in this nice paper from 2015, they showed that the naive SU2 cross U1 symmetry seems to enhance to SO5. So their evidence for this was basically that they computed scaling dimensions that naively should be different, and in fact they were very similar, and this would be the case if the symmetry was enhanced. So this is their evidence for it. One thing though, which is a bit funny though, is that usually you assume this theory is a critical theory, which means there's one relevant singlet under SU2 cross U1. But if there's one relevant singlet under SU2 cross U1, then when you enhance to SO5, that relevant singlet becomes part of the rank 2 of SO5, which means from the SO5 perspective, there's no relevant singlet. And that's kind of a very strong assumption, to have a CFT with no relevant singlets. Sometimes called a dead-end CFT. And so this conjecture was kind of immediately disproven by just doing a simple bootstrap bound, assuming SO5 symmetry, and showing that this value of 0.63 was totally ruled out if you assume no relevant singlets. I think this was done by David, who I think might be in the audience, took a few minutes. It's a very simple thing. Okay, so people were trying to think of explanations for what might be going on here. So one explanation is that maybe actually the CFT is not quite unitary due to immersion annihilation of a critical and tricritical version of QED3. So i.e. it's weakly first order. And there was some evidence for this proposal from a fuzzy sphere simulation of this SO5 theory. So there's a way of describing the SO5 theory. You write down a nonlinear sigma model, which has exact SO5 symmetry. And then you can apply fuzzy sphere to that. And then you could try to read off scaling dimensions. They tried to find evidence this past year by showing that as you change the coupling of this nonlinear sigma model, your scaling dimension of this singlet goes from being slightly above 3 to slightly below 3, which is, I guess, kind of a smoking gun for weakly first order. So this was one possible explanation.
In the context of this bosonic QED, can you say what you mean by tricritical QED?
Okay, so basically, if you study this CBN model of large N, you could also tune the phi to the 4 term to be 0. And so that's what you would then call tricritical scalar QED3. And so at large N, you have two such theories. And then you can imagine as N becomes smaller, that at some point they merge and collide and go off into the complex. Okay, but we prefer CFTs to weakly first order because we are CFT people. And so we try to find evidence that it is a CFT. And so what's our approach? So we consider correlators of SO5 of operators in the singlet, the rank 1, and the rank 2. And then after looking at these 4-point functions of such operators, this will also give us access to the rank 3 and the rank 4.
All symmetric.
Yeah, all symmetric. So this shows up in the OP. And also, we assume that there's one relevant singlet. So this is the tricritical assumption, because this implies from the SU2 cross 1 perspective, there are two singlets. We also assume there's just one relevant vector, rank 2 and rank 3, which is kind of motivated by the large N estimates of the corresponding multiple operators, which correspond to rank 2Q operators in this SO5 description. So this is a very big system to bootstrap. So there's 29 cross-chain equations, and we're scanning over 8 parameters. And so this is something you need the most up-to-date bootstrap technology. The skydive code was written by these authors in the last year. This would have been impossible to bootstrap prior to this past year. So it's really a cutting-edge study. And then using this up-to-date bootstrap code, we are allowed to show a big allowed region in the space of these parameters. So that's what Bootstrap does. It says certain values of these parameters are not allowed, certain values of these parameters are allowed, and you get some, 8-dimensional region of allowed space. So the next thing we do is that we fix the value of the scaling dimension of the rank 1 to be 0.63. This is motivated either by the large N expansion or by the Monte Carlo estimate. They both said 0.63. So we use this as an input. Then we maximize the value of delta t, and this pushes us to the boundary of the allowed region. And what's nice about boundaries of bootstrap regions is that you have an approximate solution to crossing at the boundary, which means that if you conjecture that a physical theory is at this point on the boundary, you can read off all the CFD data. So after plugging in this value of 0.63, we can read off all the other values. So the singlet, the rank 2, the rank 3, and the rank 4. Now, why might you think the physical theory is at the boundary? Well, this is something that's been observed in many other examples. So for instance, for the Wilson-Fisher theories, for every value of n, it was observed that the physical theory was at the boundary of a bootstrap plot. And even in the case of QED3 with 4 fermions, in this paper I had with Sylvia back in 2016, we also observed that the physical theory as estimated from a large N expansion seemed to be near the boundary. So this seems like a somewhat reasonable assumption that this might be the case. Anyways, so after reading off this data from the bootstrap, we get these results, and we can now compare it to these other methods. So first of all, we can compare it to the large N estimate of these monopole operators. So I read an asterisk here because this is the value we put into the bootstrap. And the other values are the ones we read off. And so it's kind of a nice check of our claim that the theory is on the boundary is that the large N estimate is quite close to the values we're finding. I mean, this is a relative error of just like 1 or 2%. So this was kind of the thing that motivated us to write the paper, this kind of non-trivial evidence that large N estimate was matching the values we were reading off. Of course, there is no large N estimate for this delta singlet, so this was a totally new prediction from our bootstrap study. So we can compare this to the fuzzy sphere. So the fuzzy sphere claimed to not find unitary CFT, which means that as they changed their coupling, they were getting different answers. But just for fun, we could choose a certain value of their coupling and just show the scaling dimensions they got. And as you see, they're kind of roughly in the ballpark of what we're seeing. The main difference being the singlet, which they find is bigger than our singlet. Because after all, as they change their coupling, they claim their singlet is going above 3. So that means it had to be close to 3 in the first place. But the other value is actually not that far, which might suggest that perhaps an improved fuzzy sphere calculation with more lattice sites, might actually, or not lattice sites, but more, I guess, sites in general, might actually get even closer to our values. The most interesting thing, though, from our perspective, though, is that a year after we made this prediction, Andrew Sandvik, who's a lattice expert, came out with a paper, which came out this past Monday, where he confirms our prediction. So he does an independent lattice simulation using something called the JQ model. And he argues that it flows to a tricritical CFT, and then he reads off the values of the scaling dimensions, and he gets the following values. So first of all, you can compare these values to these values, and as you see, they're pretty close. There's a relative error of just maybe 2 or 3%. But we can get an even better match, because remember that our values depended on this value of delta V that we inputted, because we were looking at a certain point on the boundary of the lab region. And this was motivated by large N, but large N might be off by a little bit. So imagine that we instead inputted a smaller value of delta V. So imagine we put in 595 instead of 630. Then as you see, all our values get slightly smaller, so everything kind of changes monotonically. And this is kind of changing in the right direction to match Anders's recent lattice estimate. Now, the reason why we did 595 is that Anders told us a month ago that that was his value, and then he ended up changing it when the paper came out. So this is why we didn't just do 0.607 in the first place. But I think it's actually good that we chose a smaller value, because this kind of shows the broader story. So you can imagine that if you were to kind of average these two values, you would actually get something very close to what he's saying. And so I think this is kind of a remarkable check of our conjecture, because we now have two totally independent methods, which are both giving the same answers and both saying that the theory is tricritical. And so I would also just say, for bootstrap people who might be in the audience on Zoom, assuming they're still here, I think this is a particularly interesting application of conformal bootstrap, because in the past, conformal bootstrap has mostly been studying theories we already knew a lot about. So for instance, when we got islands for these Wilson-Fisher theories, well, people already knew that Wilson-Fisher theories were CFTs. They already knew their symmetry, and they already computed their critical exponents like decades ago using lattice simulations. And so the bootstrap was just kind of like, making something a bit nicer, which is already nice. Whereas in this case, to my understanding, this is the first example of the bootstrap without supersymmetry, where we're actually finding completely new things about a theory. Because in this neo-VBS theory, we didn't know what the symmetry was, because we didn't know if it was SO5. We didn't know if it was a CFT, and we certainly didn't know the critical exponents. And so all these things were shown for the first time using bootstrap, and then later confirmed using lattice. And so I think this is kind of like a new era, where now bootstrap is leading the way instead of just following up after lattice simulations. Okay, so
can you clarify which theory this is supposed to apply to? In other words, is it supposed to apply to ordinary QED or what you call tricritical?
Okay, so that's an excellent question. And this is a subtlety, because of course at large, if you define this theory for general N, then at large N you have the CVN model and you have the tricritical. And the large flavor expansion we did was for CVN, not for the tricritical. Tricritical would have given a different answer. And so you might say, why is it that I'm comparing large N estimates done with the CVN model to a theory which I now claim is tricritical? And so I don't know, but of course, when you do analytic continuations using a large N expansion, this is a very kind of subtle thing. So like one scenario could be that you have some function of N, which is the scaling dimensions. You have function 1 for CVN, function 2 for tricritical. Then it could be that as N gets smaller, the functions basically cross over. And so the function that described critical at large N now describes tricritical at small n, and vice versa. So that's one possibility. Who knows, because after all, this is a strongly coupled theory, and this is more of an art than a science, analytic continuations to find it. But indeed, that is kind of like a somewhat kind of curious point. Now, if you want to be very conservative, you could just forget about the large N expansion, and you could just say that we did a bootstrap study motivated just by lattice, because after all, the only thing we put in was the value of 0.63, and that actually was predicted by lattice before. And then you could just say, we just put that in, we read out these values, and it was matched by another lattice study. And so you don't actually need large N. Large N is what motivated us in the first place, but you could take our results without large N, if you feel uncomfortable about the large N interpretation. Okay, so in conclusion, we computed the dimensions of monopole operators in QED3 with N scalars and turned sum level K in a large N and K expansion with fixed ratio to subleading order, which generalized previous results for zero turn times level. After extrapolating to 1n and k equals 0, we use this to check particle vertex duality. When we extrapolate it now to k equals 1, we use this to check 3D bosonization, which is the first dynamical check of 3D bosonization. The check so far only works for the special values of Q, which are unique scalars, but there's this intriguing connection to the large charge expansion for general Q. Finally, when we also take the large flavor expansion for n equals 2 and k equals 0, then we found that these large N values satisfied an SO5 bootstrap bound, which suggests that the neo-VBS phase transition is tricritical, and we give a prediction delta S equals 2.36, a prediction that was confirmed last week by an independent lattice simulation. Future directions is, first of all, it would be nice to improve the large N calculation of monopoles for the non-unique scalars, because there could be some subtleties. Maybe you have to look at a different saddle, for instance. Similarly, it'd be nice to actually have an analytic proof of 3D bosonization in the large charge expansion. This seems kind of suggested by our results, but it'd be nice to actually show that analytically. I think that would be remarkable if you could prove it. Thirdly, this monopole calculation is very general, and so there's a lot of generalizations that one could do. So for instance, first of all, you could generalize it to QED3 with n fermions in non-zero K, and there's other dualities you could check. This is something I've been working on with one of my collaborators. Unfortunately, my collaborators left physics, and so the work has gone very slowly, but hopefully eventually we will finish. You could also generalize it to n equals 1 SQED3. There's other dualities in that case. Finally, you could look at QCD3 for some finite values of the rank. There's yet even more dualities in that case. So there's a huge family of these QCD3, QED3 theories, of which you can do multiple calculations and check all kinds of dualities. And so I hope to motivate people to look into this, because these calculations are challenging, but they're not too challenging. And so if someone's interested, I'd be happy to kind of show them the literature and get them started. Finally, what's nice about this neo-VBS phase transition is that in principle, it could be experimentally probed. And so it would be really nice if someone did an experiment, computed these scaling dimensions, and matched them to our prediction. That would be very exciting. Finally, there's kind of a somewhat similar story of QED3 with 2 fermions. So in this case, it was conjectured by these authors that, as well as other authors, I think I'm missing some papers, that the symmetry is supposed to enhance from SU2 cross U1 to O4. And so the original version of this proposal was that the theory was critical, which means under O4 there was no relevant singlets, and that was again kind of ruled out by bootstrap. But it might be that a similar story is going on in the O4 case as is going on in the SO5 case. So it might be in the O4 case, maybe actually the SU2 cross U1 is tricritical, such that the O4 has one relevant singlet that would avoid the bootstrap bounds, and then you're just be kind of analogous to what we saw in SO5. And so maybe this is like a generic story that whenever you have kind of like enhanced symmetries in the IR, for some reason, the theory becomes tricritical. So this would be kind of an interesting thing to look into. Yes.
Critical here, you mean gross noble QED?
Well, okay, again, so this relates to Thomas's question, which is that like at large N, there are two theories you can define, gross noble as well as regular QED3. Now, usually when people talk about this O4 symmetry enhancement, they are referring to regular QED3 with two fermions. But there might again be this kind of funny thing, which is that if you compute multiple operator scaling dimensions of large N, the analytic continuation kind of switches between critical and tricritical when you go down to smaller. And like, because that's kind of the same story, I guess, which might be the case in the CPM model. Because like we're kind of claiming the CP1 model is tricritical, even though you would say like, oh, but tricritical is a whole other family of theories. But it might be that when you analytically continue to the strongly coupled regime, they somehow like switch identities.
But isn't the worry that if this crossover happens, then somehow you've passed the point at which the fixed point might annihilate?
Yeah, I mean, but that annihilation, maybe it happened for some fractional value of N, and this is why, like,
That's true, but then for lower values of N, you're somehow.
Well, okay, so they go into the complex plane and they return to the real plane. This could happen. I mean, like, it's like all kinds of things like this could happen. I mean, it's a strongly coupled physics, who knows? Like, it could be they go back into the real plane. It could be that one of these theories just like disappears because like it goes to zero, like the OP coefficients go to zero, like all kinds of things could happen. Certainly unusual, but then again, this is clearly an unusual story.
Do they even need to go into the complex plane? Like Wilson-Fisher and the Gaussian fixed point merge as you go to T equals 4 and above, and then you just have the Gaussian fixed point afterwards.
Yeah, I think it's special to merging with free theories, though.
No, but he wants a scenario where you start with two fixed points, then they cross, and then you are only left with a tricritical one and nothing else. So that's
no, but that would be analogous to what Ryan is saying, because it's like in the Wilson-Fisher and free theory case, they merge.
Coupling is different.
No, I understand it's different, but I'm saying that like at least the sense of two going to one is similar. I understand in this case it's not going to zero coupling, so it's it's a bit more novel. And so like I would maybe try to argue that like they go like one of the theories is a sense of disappearing and only one survives, which could happen. There's nothing stopping that from happening.
Sorry, so gross noble QED was supposed to run to SO5, right?
No.
To some literature.
Oh, sorry. Okay.
Right.
Sure. That's something else. Yeah. Okay.
Right. So if this is correct, are you saying that it's enhancing only to O4?
No. I guess what I'm just saying is that what you call QED3 with two fermions is related to what you would have called gross noble at large N. But I'm saying the identity changes. I mean, it's always kind of a philosophical question. It's like, what does it mean to say that it's that theory? Because when N is finite, it's a strong coupled theory, and you can't get too much from the Lagrangian. So it's like the claim is like
the question is still well defined.
The question
I might be able to answer it.
Sure, the question is well defined, and my claim is that there'd be kind of a crossover in these identities, which there seems to be some evidence for by comparing lattice to large N.
I also don't understand why, as you tune a parameter, a operator can't just become relevant just as a function, and like in the KT transition, right?
It can become relevant, but I think usually people argue that like because there's that some point where it's exactly marginal, and because it had to become marginal at some point, those kind of funny things happen at that point.
But this doesn't happen in like a KT transition.
You're saying in that, I want to see if people are asking questions on the Zoom. How do I see if people are asking questions on the Zoom? Or I guess you would see it.
Nobody's
asking. Okay. Okay, so there's one last slide. I added the slide for Ryan's benefit so there'd be a new slide. But this is a question you could ask. People are talking about like, oh, have you computed the subleading terms in 1/n? And so there's a special case where one can compute those subleading terms. This is for BPS monopoles for 3D n equals 2 QED3. So in this case, you can compute the answer exactly using superspecial localization. You can also compute it in a large N expansion. And so this is a way of checking the large N expansion. So this is what we do in this plot here. So the red values are the exact values. Gray is a leading order, which would just be a straight line. And then blue is including the first correction to leading order, which is basically what we did. And so as you can see, it's like a pretty good approximation, even down to n equals 1, because this axis is like fairly small. And then once you include the sub-subleading correction, which we didn't compute yet, but in this case you can compute, you see the match gets even better. And so like one of the lessons of this paper, as they discuss, is that it seems like this large flavor expansion is a convergent expansion, which is unlike expansions using Feynman diagrams of conventional operators. So there's clearly something very different about monopole operator scaling dimensions, which you can check in the one case where you can do the calculation exactly. Now, this case is a bit different from the non-supersymmetric case. First of all, because in this case, Q is just an overall coefficient. Because basically the way the calculation works is that the scaling dimension is proportional to the R charge. And so the R charge, you can just add R charges for different values of Q. So Q doesn't enter in a non-trivial way as it would in the non-supersymmetric case. And also like N is also a bit trivial in that well, not totally, I mean, the large N expansion is non-trivial, but it's like, you can also look at different monopoles. Well, sorry, I forgot about N. Yeah, so the non-trivial thing is Q. So it's not completely analogous to non-supersymmetric case, but hopefully there are some lessons in that the large N expansion certainly seems to work very well. And so this, I think, does motivate people to compute the next correction in 1 over N, because I believe the expansion will be convergent, and I believe that you will find that that coefficient is extremely small. And so this would be particularly interesting to do for the case of k equals 0. Because in that case, when we had this table, we saw that the subleading term was bigger than the leading term, but if this expansion is convergent, that suggests that this is just some kind of quirk, that it happens to be the second one's bigger than the first, but I expect that the third one will be super small. And so that would be something which would be very nice to check explicitly. And the calculation is possible. All the tools are there. It's like the monopole spherical harmonics are there. It's basically just a matter of just like basically doing Feynman diagrams on S2 cross R, which I think should be possible. Okay, so are the Zoom people still here?
Yeah.
Okay, so any questions from the Zoom? I guess.
Yeah, I have a question.
Okay.
So in this study, this lattice study done by Nahum et al., where they suggested the SO5 enhancement.
Yeah.
What's the explanation for why they didn't think there was a relevant singlet in that
Okay, so that's an excellent question. Is that you could say, like, why is it that they thought they got to a fixed point if they were only tuning one parameter? Because tuning one parameter implies that there wasn't this extra singlet. And so this is a question for lattice people. So I spoke to Anders about this, and he discusses this in his new paper. And like, he has some kind of lattice explanation, which I don't claim to fully understand. But I think he's basically arguing that, like, they were kind of like coincidentally very, very close to the tricritical fixed point. And this is why they didn't really have to tune a second parameter so much. And this is why they got answers that actually were pretty close to the right answers, even though they only tuned one parameter. So basically another way of saying it is that they were just not very sensitive to the second relevant singlet. Now, the second relevant singlet is relatively big. I mean, it's like we claim it's dimension 2.4. I guess Sandvik claims it's dimension 2.3. And so that means that its effect is not huge, although it's not like it's 2.9 though. But in Sandvik's paper, he gives a more complicated lattice argument for why he thinks that these people just didn't encounter it. Because his lattice is actually very similar to the one Nahum is using. So it's like, there's kind of two models, like Sandvik has his JQ model and Nahum has his loop model. But from what Anders says, these models are like, I think in some sense kind of equivalent. And so that's why I think if one were to redo the loop model calculation, I guess Anders would claim that they should actually see that it's tricritical and they would get the same answers he did.
So it's just this issue of not going to big enough lattice, or?
Yeah, probably, yeah. I mean, in Sandvik's new paper, he goes to an enormous lattice. I think it was like 1,000 lattice sites or something, which like, I think only Anders is capable of doing that. And so, which I guess was like necessary in order to get these kinds of like precise estimates and to be kind of sensitive to this, second relevant singlet. So yeah, I encourage everyone to look at Anders's paper, which came out on Monday. Which is a tour de force of lattice calculations.
Yeah, there were some weird puzzles in Nahum's paper, I remember, where they had some data that looked like it actually hadn't converged, like it wasn't really scaling in the proper way for a CFT. But so they had to do a kind of non-standard fit to extract their critical exponents. So that was kind of weird. But another confusing thing was, if there wasn't a CFT, then how on earth could there be symmetry enhancement? Like you cannot have symmetry enhancement without a point that the theory is scaling towards.
Yeah.
This scenario, I guess, explains that, because they weren't at the CFT point, but the violations of conformal symmetry were by an SO5 singlet. So the violations of SO5 those were all irrelevant and scaling to 0.
Yeah, so in Anders's paper, he actually discusses a lot of kind of weird features due to the fact that there's an enhancement of symmetry and that it's tricritical. So when you have both, this leads to new lattice phenomenon, which have never been observed before, because I guess no one ever had a theory which had both. So in particular, I mean, you should take a look at his paper, but so he had like 2 versions of the paper. One paper came out before our paper, and it had some answers that were wrong. And then he kind of fixed that as a result of our paper. In particular, in his original paper from, I guess, a year and a half ago, or 2 years ago at this point, like he was claiming that there was some operator with scaling dimension 0.8, which we just don't see any operator of that sort in our study. And so it turns out that he wasn't actually seeing that operator. This is some RG effect when you have symmetry enhancement due to crossover. And so the correct interpretation of this observable is that it actually is corresponding to a different scaling dimension, which you can relate to the scaling dimension he found by some exact formula. And so that transforms the 0.8 into this 2.2, which is then much closer to what we were finding. And so, yeah, so I mean, from a lattice perspective, it's also kind of cool because there's a lot of new features.
Thanks.
I have another question. Hello.
Sure.
It seems to me bootstrap value more or less agree with the lattice, but for fuzzy sphere, delta S is quite far from both bootstrap and the lattice. And also in Ziyang's fuzzy sphere study, they also get pretty big delta S. Do you have any?
Yeah. So first of all, I just to be clear, this fuzzy sphere data is Yin-Shen's study. So there's actually 2 fuzzy sphere studies, one that came out also a week and a half ago by Ziyang Meng, which is kind of a further development. So actually the new fuzzy sphere calculation by Ziyang Meng claims to find a tricritical theory similar to ours, but the scaling dimensions he gets are similar to what Yin-Shen got, which claimed there wasn't a tricritical theory. So I guess it's kind of going in the right direction from my perspective, but the scaling dimensions are still a bit far away. And so you could ask, okay, why are these scaling dimensions so far? I mean, what's weird is that some of them are close and some of them are far. Now, I'm not an expert in fuzzy spheres, so I don't fully understand why, but with fuzzy sphere, usually they're only kind of doing a very small number of sites. And so I think they're doing something like 6 or 7 sites or something. And so it's and they use exact diagonalization. So it's kind of surprising that they're able to get as good answers as they do, considering there's so few sites. Whereas Anders is using 1,000 sites. And so it might just simply be the case that their answers just haven't converged and that they're very far from convergence. I mean, after all, the only example so far with fuzzy sphere where it gives good answers is the IC model. For the IC model, fuzzy sphere gives amazing answers. But even for 02 and 03, from having discussed with some people who are working on that, I had some email correspondence, even in those cases, it seems like they're having trouble getting very precise answers. And so I think at least so far, it seems kind of challenging to scale fuzzy sphere beyond the simplest IC model case. And that might just be what they're observing in applying fuzzy sphere to this non-linear sigma model. I mean, it could also be that this non-linear sigma model is just not the best description of this theory, which is another possibility. Although it's intriguing why they got at least some of the scaling dimensions to be in the right direction. But it could, maybe there's also some story that the bigger the scaling dimension, the harder it is to get a good estimate. Although I guess this would kind of violate that intuition. But I mean, who knows?
Thanks.
That's my collaborator, by the way, Nate. So.
Are there other questions for Shai? Let's thank Shai for the nice work.